All right. So now we're on to Unit B. Okay, Unit B of the data booklet, and this time I'll be focusing on mainly on going through the formula and explain what they mean. Okay, I'll not do too many sample questions as I go because that delayed a little bit on the previous video, making it a little bit long. All right. However, this should give you a rough idea, a little bit of review, and catch up, and just get you familiar once again with the stuff you hopefully have learned in class or about to finish up for your prior to your IB exam. So, without further ado, let's get started. First one, okay, first one, right here. Oh, what? There we go. First one right here is everybody very familiar with. This is density, the density formula. I will not actually quite explain what it is because these are all symbols that's used pretty common previously. Okay, so mass per volume. Okay, bigger the mass. Okay, in each volume, the more dense it is. Smaller volume, more dense it is as well. All right, so that is just basics. That's useful for help us calculate the mass or volume of something that's also indirect. What's really interesting to us is how to observe things both from a microscopic and macroscopic point of view. All right, in the first unit, we'll mostly look at things from macroscopic perspective. Okay, in B.1 and B.2. And in B.3 and B.4, as we'll see later, it's more from a microscopic perspective. But the second formula actually links the macroscopic and microscopic together by looking at the average kinetic energy of particles in anything. All right, so I'm type it in. This is the, over here. Here it's the EK. It's a mean. Notice the mean EK is the mean kinetic energy of particles in a substance. Here, Kb is one of the constants. It's Boltzmann's constant. And T is temperature in Kelvin. Now, this Kelvin here is absolute temperature, right? So maybe we should say that. Absolute temperature measured in Kelvin. Okay, that's very important because you can actually know how to convert from degrees Celsius to Kelvin using the formula conversion factors in the front. All right, so that is the second formula here. I wonder, I'm thinking about it. I can probably change color too. No, it's okay. Red, orange. There we go. All right. Now moving on, for those in the Alberta curriculum, okay, this formula should be very familiar as well because this formula is probably learned in Science 10. Those are the heating formulas, okay, the heating formula. Okay, the first one is when an object is being heated up or cooled down, okay. So Q, of course, always here is a change in, it should be change in thermal energy, which is heat. So Q is heat, which is change in thermal energy. Usually denoted into delta Q, but I'm just gonna leave it as heat. Okay, leave its Q here as used here. All right. Now, for the first one, this is change in temperature. Okay, so the first one is when something's being heated up or cooled down. So it's heating up and cool down. Then we use the specific heat capacity. And here, delta T is change in temperature. You'll notice I didn't write a formula for this one. I didn't unit for this one because either unit for Kelvin or Celsius would work for delta T because they actually have the same scale. They have different values, but they have the same scale. However, if you are phase changing, then all the energy does not change temperature. All the energy actually goes into the potential energy of the particle. As you notice, temperature is kinetic energy, right? So it's no change in temperature. So L is a specific latent heat. Or specific latent heat. Alright? But both give you the value for heat absorbed or extracted. Okay, so remember, that's why I usually present it as delta Q. Okay, delta Q here, this one. Alright, same thing. Once again, over here, delta Q is the amount of heat on thermal energy transferred. Okay, so the next one is the next one is about thermal energy transfer. Alright, transfer. Specifically, this is thermal energy transfer in conduction. Can I fit over here? This one is thermal energy transfer by conduction. Alright. Delta Q, of course, once again, is heat. How much energy is transferred between one or the other. So the first one is actually just power, the transfer power. Okay, so the first part is just transfer power, okay, or transfer rate. Equal to blah, blah, blah. Equal to formula. Okay, so K here, okay, K here is what we call, not Boltzmann's constant, that's Kb. K here is thermal conductivity. It depends on the substance. Different substance will have a different K value. A is the cross-sectional area which the energy transfers through. So it's cross-section area. Cross-section area of the object, or more specifically conductor. We like to imagine when two things are transferred by conduction, they're not so much touching directly. They usually have a conductor in the middle that mediates it. So they touch indirectly through a mediator in the middle. That mediator could be air, but we pretend it's solid. Alright, and we just let the lengths go to 0. Alright, so on the one end, you have a hot end, you have a cold end, energy go from hot to cold, and how fast that energy flows from hot to cold is the rate of transfer we're calculating over here. So you have a conductor in the middle, okay, and energy flows through the conductor. We'll assume the conductor is what we call a state of, shoot, I'm escaping my mind right now. I'm gonna look at my notes quickly here. In a state of steady state, which means its temperature does not actually change, energy does not actually lost in the conductor, energy goes straight, effectively, energy goes straight from hot to cold. It's just a conductor help us regulate the rate. Excuse me here. Delta T over Q here is what we call temperature gradient. Okay, that's what we call temperature gradient. Basically, how much temperature differs from incremental distances, right? If you have a longer distance, you'll take longer, the rate will be slower because the difference in temperatures can be smaller per increment. However, if you have a really big temperature difference, that may overcome that. So you have to count for both. So we call that temperature gradient. All right. So that is the formula right here. You can call it a conduction formula, but really it's a transfer rate formula for conduction. I guess I should add the word for conduction. For conduction. Oh, what? Click wrong spot. For conduction. There we go. The next two are actually relates to what we call Stefan-Boltzmann's laws. All right, Stefan-Boltzmann laws. All right, I'll write them over here. I'll write them separate. But write both of them on the right side. This one is a Stefan-Boltzmann law. Actually not slaw because there are two people. Stefan-Boltzmann law. Okay, here L is actually a different symbol for power. That's because it's radiating power. Okay, it's how much energy is leaked out and the way we interpret that energy is how bright it is. For a black body, everything it absorbs, you radiate back out in the form of EMR. So that's why we use L here, because EMR, light, is something we see. It's luminous. So L here is actually power. You can use P. P is correct. But we call this luminosity or luminous power. Because, once again, for a black body, its energy is released in the form of light. Alright? Sigma here is the Stefan-Boltzmann constant. You can find that at the front page. Hang on the front page. A is the area energy is leaked out, usually the entire surface. Okay, A is the area energy is being exchanged. It's released. Usually surface area. However, as I'll mention in a little bit, it's not always. And T is temperature. T is absolute. Alright, now, for a black body, because a black body absorbs everything and releases everything, this can also be used to calculate how much energy is being absorbed by a black body. Okay, it can also be used to be calculating absorbed. Can also be used to calculate absorption power of a black body. Alright, BB. Alright. In that, however, the only difference is when it's absorbing power, it's not luminous. You should use P instead of L. And the surface area will only be in the area that's being heated. The side that's absorbing the energy. And the temperature of the side that's absorbing the energy. Right? The temperature and the side. So the area may change. So that's why I say A is usually a surface, but the black body may not be absorbing its energy through the surface all the time. For instance, the question you will see, of course, when the sun arrives on Earth, Earth actually receives energy on a cross section and emitted them on this entire surface area. Which brings us to the next thing. Next is called the intensity formula. Okay, intensity formula. Okay, I'll write it right behind. Intensity formula. Alright, B here is intensity, which is equal to power per area. You may notice that's just sigma times T to the fourth. That would be correct. If you are on the surface of an object. Okay, so how bright is the surface of the sun? Sure, sigma times temperature of the sun to the fourth. Done. Okay, done. However, this does not work for things in general. So this has to be more generalized. That's where this formula comes from. Okay, the P over A. All right, and P, of course, is luminous power. That won't change. Okay, that won't change. Excuse me. But if you are D distance away, D is actually distance from the center of the black body. Alright, which means, alright, you may be able to use sigma times T to the fourth to calculate if you're on a surface, but if you are way off, like you're over here, like this is the sun, the black body, let's say, you're way out of here, then you actually have to calculate the entire surface area because radiation goes in all directions, right? So you actually have to take the entire sphere, to calculate. Okay, to calculate the luminous, the intensity. All right. Intensity has another name, of course. It didn't use I. Well, I is confusing because it shows up quite a bit in this unit. Because once again, we interpret intensity as brightness. So that's why it's little b. All right. So just know that you are expected to know that this formula is actually talking about intensity, and intensity is actually power over area. Power over area. Once you have intensity, you can actually measure intensity as and wavelengths. This is what we call Wien displacement law. I spelled its name wrong. This law simply tells you what is the peak wavelengths at different temperatures, because at different temperatures you actually get different intensity graphs. This basically goes through the peak wavelengths. Peak wavelengths at a given temperature. What's interesting is peak wavelength is always less than UV, okay, and the amount of higher than UV light is always smaller, and that's not predicted by the classical model, which led to the UV catastrophe. That is what's talking about. Wien displacement law, okay, actually summarizes the wavelength is always less than UV, but theory says it should be X-rays or gamma rays, something else, and that is contradiction. It's Wien displacement law. Factual observation disagrees with the prediction of classical and Maxwell's equations. So that's what led to the development of quantum physics. So it's all related to each other. It's all related. All right. Greenhouse effect is a very short lesson, okay? Mainly because greenhouse effect actually uses all of these formulas. Actually, not all of them. Mainly the last three formulas. Energy transfer from radiation, black body radiation. That's where it comes from. So energy comes from radiation. However, okay, not everything is absorbed. Not everything is absorbed. So not everything's. That's what I meant. Not everything's. Yes, correct. Not everything is absorbed. Therefore, not everything's emitted. Okay. So the amount that's actually absorbed or emitted, okay, is called emissivity. Okay. So it's power radiated per area times per unit area over sigma t to the fourth. Or you'll notice if I simplify this, okay, I don't have to explain the formula because everything's here. If I have to rewrite this, you'll get, I don't have to write it. I said I'll rewrite it, okay, because symbol. You'll notice this one actually becomes the power, radiating power is equal to E times sigma A t to the fourth. This is a real Stefan-Boltzmann law. The general, may not real. This is not the real. Both are real. This is a general Stefan-Boltzmann law. All right, general. So this, what makes this quite interesting? What makes this really interesting is this means that an object could be having a higher temperature, Earth, than its radiating power indicates, right? This is radiated power, radiated. So once again, if Earth is a black body, it should be radiating at a lower temperature. Given that how much energy is radiating back out, right, coming from the sun and then absorbed, radiating back out, right, it should be radiated. It should be a lower temperature. Won't let me write. It's got R, radiated. Okay, radiated. Okay, radiated power. The Earth, given how much energy is radiating back out, which is basically most of the sunlight is coming in, okay, it should be a cooler temperature. It's a cooler temperature. Okay, but the Earth is actually way warmer than that. The reason being, the Earth actually have a self-heated engine called its mantle, and it also has greenhouse effect, traps some energy from the sun, okay, to keep it warm as well. So not only is it not radiating all the power it's coming to it, it's actually radiating less power even if it does, because that generates its own energy. So an object can be actually hotter than what it appears to be. Okay, so that's what emissivity is telling us. It's possible for an object to be way hotter but appear to be cooler. So that's what emissivity is all about. Albedo, on the other hand, is something similar, related, but not quite the same thing, or not even the opposite thing, but it's related in the sense that albedo is just the proportion that's reflected. So a bunch of energy coming in, okay, you'll get it reflected back out. That's called albedo, all right? The the portion that's reflected back out is going to be what albedo is trying to indicate. For solid, one can make the argument that albedo must equal to 1 minus emissivity. It's not generally true, but it is a good estimate. Okay, that albedo and emissivity add up to 1. I will not write it here because it only works for solid, and we're only dealing with solid things. And when I say solid, Earth is not solid enough because Earth has an atmosphere. An atmosphere is made of gases. So atmosphere is actually responsible for most of the albedo on Earth, which means we cannot actually use this formula. So I'll not write it down, but it's a good estimate, not what it actually is. The emissivity and albedo add up to 1. Once again, it's a good estimate, but that's not what it is. So albedo basically reflects a bunch of energy. Those energy never arrives on Earth. All right, never arrived on Earth. Accounting for those that didn't arrive on Earth, okay, we see how much get to Earth's surface. Now, if we treat Earth's surface as a black body, all those energy should reflect back out. But even we account for that, Earth is not hot enough. That's because that Earth doesn't actually let all those energy leave, and also Earth generates its own heat. Earth generates its own heat. So combining both factors, Earth ends up being warmer than how much energy it's actually letting out. All right. So anyhow, that's what it is. That's greenhouse effect review. That's all there is to it. All right. Next part is the gas laws. The gas laws is learned in Alberta's chemistry 20 question mark. But chemistry class. So there's actually not too much talk about. Not actually, there's quite a lot to talk about because I'm pretty sure that chemistry only covers this much. I'll say it first because to get it out of the way, because everybody knows what this is so popular. Everybody knows about it. There's memes everywhere about it. First is what we call empirical gas law. Okay, the empirical gas law is what we found through experimentation, which includes the Boyle's law, Gay-Lussac, and I'm forgetting one person, and I'm blanking out right now without looking at my cheat sheet. And let's see here. Load up my cheat sheet here. It's kind of silly. Gay-Lussac, Boyle's law, and there is one more. I know there is one more, and I need to look it up on my cheat sheet. And it's not on my cheat sheet. Thank you. Let's see here. Boyle's, Gay-Lussac, Charles's. There we go. Charles's law. I blank out. Charles's law. All three are experimentally verified, so these are called empirical laws. The empirical law only conclude that PV over T is a constant. Okay, that's all they tell us. That's all it is. That's all he knows. All right. Avogadro come along and says, well, I think volume is proportional to the number of particles it has, moles. So Avogadro come up with the last one. So with Avogadro's law as well. With Avogadro's law, which is not experimentally verified, so it's an ideal law, it becomes the ideal gas law, which is PV equal to nRT, the famous one, this part, PV equal to nRT. However, with Boltzmann's definition of his constant, okay, Boltzmann's constant is exactly the gas constant over the Avogadro's constant. So Kb is equal to R over Avogadro's number, A, which is 6.02, actually Na. 6.02 times 10 to the 23. Okay, so with that definition of Boltzmann's constant, which he's trying to model for his kinetic energy and behavior, you get the formula which you see in front. Okay, That, once again, is just the ideal gas law. So those are the empirical law on top and ideal law on the bottom. Okay, ideal law on the bottom. All right. Now let's talk about the peripheral things related to it. Okay. First one is the first two are basically the fundamentals. Okay. First one is talking about pressure. Definition of pressure. Pressure. Well, I'll say P is pressure. P is pressure here, and F is a force. Oops. Force applying over surface area. So I'll write definition here for the letter because it's not a. Well, I think we've seen them before, but I'll still write it down. X is force. A is area on the force. There we go. Now, when it comes to gases, once being the gas unit, it's basically how much area are the gases pushing, right? There's a lot of gas particles pushing on the wall. You have a bigger wall, same amount of particles, you're going to have a less pressure. Bigger wall means bigger volume, so bigger volume, less pressure. That kind of stuff, right? So that's what pressure comes in, because we assume the particles are applying the same force no matter what. It's just if a bigger area, the pressure the force actually applies is going to be smaller. Second one is, once again, classic. Okay, classic. This is not even like a formula. This is just definition once again. Both the first two are definitions. This is the definition of a mole. Mole. Okay, mole is the number of particles and Na is Avogadro's constant. Avogadro derived this number, okay, from his estimate, okay, calculation, all right. I don't think he actually derived the number. I can't remember the history. I digress. Doesn't matter. Avogadro's constant basically indicates how many particles there is in 1 mole of a substance. So number of moles, just like take the number of substance divided by the number of moles. That's it. All right. You are not in chemistry, so you do not have to know some things like molar math or stuff like that. But those are considered prior knowledge still, and it may be referenced. Someone will test you, but a molar mass and stuff like that may be referenced, but not tested. Okay, not directly tested, or unless I tell you, I'll explain it to you. All right. So combining those things together, we can actually calculate the following things. For example, the pressure and the internal energy of a system. All right. So for this one, this is pressure. Pressure can be calculated from its density. From its density and its root mean square speed. Be careful. This is a root mean square speed. Okay. I'll write it down. So P is pressure. Okay. Rho here is density, as we've seen before, and V here is actually the root mean. I changed from equal sign to subtraction. Didn't even notice. Equals. Root mean square speed. And root mean square speed, I will not drive it here, but it's actually what we mean by quote-unquote average speed, or we normally talk about particles, okay, because so many of them and how they relate to kinetic energy. All right, so we can actually calculate pressure this way. Basically, we use formula for kinetic energy and a conservation of momentum, and of course the pressure formula. All right. So you can calculate pressure. Well, do be careful. This is for all for ideal gases. Okay, this is all for ideal gases. Especially the case for last one. Last one, I should really call it the total EK. Okay, total EK. But for an ideal gas, total EK is all the energy there is. For a gas, there's no, or assume, for an ideal gas, there's no EP or total internal energy. Which means, which will assume, star, ideal, no EP. Very important. This formula only works when there's no EP. So basically, you take the formula from way up here, this one you see, this one, just EK, period. Okay, it's just EK, there's nothing to do with EP or EK, there's ideal gas or otherwise. That's the average kinetic energy. And then you say, okay, if that's the average kinetic energy, what happened if we multiply it by number of particles? So, I will not, the variables here are, we've seen before, so I'm not explaining the variables, I'm explaining where they've come from. So basically, this one is just, I'll zoom in. U is equal to, once again, we're assuming there's no EP, so it's n number of particles times the average EK. What? Average EK. Alright, which is n times 3 over 2 K. Why are there hidden things everywhere? K B T. And that's where the formula should come from. Oh, scroll down too much. There we go. All right. That's B3. That's B3. All right, up on the B4. Well, we don't do B4 actually because B4 is higher level. So B5 is actually next one on the list. Okay, even though I think B5 have some a higher levels. Oh, it's probably not formula related. Okay. So next is B5 because B5 is not higher level. B5 is standard level mostly. All right. So these formulas are actually a little bit different from the rest in that these are all new notations, but they use some similar symbols. So I'll just explain what they are. Okay, there's not actually too much to explain here. First one is current. Okay, first one is the current formula. So I is current. Q is charge, so change of charge, delta Q. Flow of charges, amount of charge change, amount of charge moved through a given point, and delta T is time it took. Alright, time taken. Alright, second one is definition of potential, electric potential, or potential difference rather, voltage. As we'll learn later. Okay, well, W is the amount of work done. Also, change in energy. Sometimes the question might phrase it as a change in energy instead of work. How much energy is changed? As for the, you will remember in the later unit, I think it's actually unit 3. This 3 is fields, right? Well, 3 or 4. One of them is fields. We actually talk about delta E is actually changing potential energy we're talking about here. How much potential energy is gained or lost. But here we'll just say how much energy is done by the whatever the circuit is done. Alright, and Q is charge. Q is charge. So for each charge, how much work each charge is doing. Right? That's voltage or potential difference. And then once we know how much energy is being used and how much energy each charge have and how many charge you have per second, together we can calculate, well, how efficient in a sense. Okay, not what efficiency is not a good word, but how much energy is really going on. How much energy is really being used, how effective it is. We call that resistance. Okay, if you have a lot of energy, okay, and very little current, good. You're doing a lot of work with a little charge. That means you have very little resistance. If you have a lot, I got it backwards. If you have a lot of energy, if you need a lot of energy but a little current, then you must have a lot of resistance because you need a lot of work to do it. If you have almost no voltage, barely any energy, but you have a huge amount of particle going through, that means you're not resisting it. You're just letting particles coming through without any effort, right? So that's no resistance. I got it backwards. So if you have a lot of V If you have little I, you have bigger resistance. You have little V, but a huge amount of I. That means you have really low resistance. Okay, low resistance. So this is called resistance. R is, and I think I just say lots of V means lots of R. Otherwise, that's why you need a lot of energy to go through it. Okay, and lots of current means you don't have a high R because you don't receive any resistance. Charges can go through without much trouble. Okay, without much trouble. You can actually calculate the resistivity of a substance. Okay, experimentally. This is discovered experimentally by relating to its cross-sectional area and length. Okay, but rho here is not density, but resistivity. Resistivity, okay, it's different by substance Okay, different substances have different resistivity. The bigger resistivity, the more resistance you will have. Okay, A is cross-sectional area. Okay, the bigger the area, you have less resistance, right? Because more charge can flow through more easily. While longer, what means charge has to follow a longer distance, receive more than resistance all the way through, so resistance will increase. So length of resistor. I should probably say for all of them. Of a resistor. Alright, so basically the formula that's actually of use here is R is equal to rho L over A. That's quite useful because you can use this to calculate resistance. Combine all the formulas together, you get the formula right here. Okay, combining all the formulas together, you get this formula right here. Just know that you actually combined Ohm's law here without doing too much. Ohm's law is not the same as the formula. Ohm's law, oh, not right here. Ohm's law says a change in V is equal to R times change in I, which means if you graph the VI graph, usually V is there, I is here. Doesn't matter though. The line should be linear. Okay, that's what it means. Now, most resistors do not do this. Okay, does not do this. This just means resistance is constant. R is constant. It is not to be mistaken as definition of resistance because resistance is always equal to V over R, V over I, but it's not letting me zoom in. There we go. Erase this. Not me writing these. Okay, R is always equal to V over I, but if it's the same, then as I changes, V will change the exact same amount of 2. Ohm's law. Alright, that's actually something I should mention. Ohm's law is not, this is not Ohm's law. It's the definition of resistance. But if you combine all of these together, no, not the last one. These three together. Alright, and plug into power, you get these two for free. So here, power is just I times V. P is power. Now, to get P equal to I over V, you can just use definition of power, which is energy over time. Energy over time, just add charge in there, then you're done. Right? Charge over time. So power, you can drive that as well. But you can actually use Ohm's, well, I should keep saying Ohm's law. Using definition of resistance, we can actually find the remaining two formulas. So all three of these calculates power. Then you have properties of the circuits, series and parallel. Okay, parallel and series circuits. And then, so in series, this is behavior of series, behavior parallel for currents, voltage, and using, once again, using R equal to V over I, which is always true, using R, I'll type it, R equal to V over I, you process through, and then you will get the R formulas down below, the resistance formula down below. All right, these are called Kirchhoff's law rules, Kirchhoff's laws. Okay, so Kirchhoff's laws. All right, current are called junction rules, and then voltage are called loop rules. Okay, make sure you review that. I will take a little bit lengthy to explain in detail here, but make sure you review this. Ooh. And that will be covered. Last is what we call the internal resistance formula. Internal resistance, because a real battery doesn't have, it's not resistance free. Okay, it does have some resistance inside the battery. So R here is the internal resistance. All right, and R is what we call the terminal resistance. I move it over here, more space on the left. Terminal means actual, not actual. The one we measure. This is one with circuits. All right, and epsilon here, or a little e here, E, I guess. This is the EMF, which is equal to total voltage from the battery. Not the voltage you measure. We cannot actually measure EMF. There's a specific experiment we can do to measure the EMF, which is probably mentioned in your notes. Make sure you review it. But EMF is not something we can actually measure, okay, because of internal resistance hidden inside. All right. So if you want to modify this formula, you actually get it's equal to V terminal plus IR, where V terminal is equal to IR equal to the voltage you measure. We can measure, which we call terminal voltage. Okay, terminal voltage, the total voltage. So all the formulas above the V we're talking about in the Kirchhoff's rules, these, well, I shouldn't say that because you can include internal resistance in there as well. No, I'm not saying anything about it. All right, but I'm just saying all the voltage we actually measure, okay, and we actually measure and calculate with is the terminal one. Okay, the internal one we have to calculate it or measure it indirectly. Finally, wrapping up additional higher level topic in Unit B, which is thermodynamics. Okay, thermodynamics. Right, thermodynamics is actually application of B.3 gas laws. So not so much circuits. Okay, so there's a weird jump here in formula, but do pay attention to that when you are using this for your tests or studying. All right. Now, this is actually not a great deal to talk about except definitions, because most of these are just telling you relationships between different things. All right. So this one is just the first law of thermodynamics. First law of thermodynamics. Which says Q, the thermal energy added, heat, the thermal energy added or removed from a system will have to either change kinetic energy, internal energy, basically. Remember, we'll assume there's no potential energy, so kinetic energy is internal energy. Or make the gas do work some other way, which is expanding or shrinking. Work done by the gas on the environment. Now, of course, if the gas is shrinking, it's not doing work to the environment is doing work to it. So if it's shrinking, then it's negative. it's expanding, then it's positive, right? So positive expand, negative shrink. Okay, I'll put it down another line over here. There we go. All right. Now, to calculate how much work it's done, we can actually use this idea of P delta V. Now, just be careful. This assumes temperature is constant. If we assume temperature is constant, right? PVT. If we assume temperature is constant, we can do that. So it's pressure, work done, not temperature constant. Pressure is constant. That's what I meant. Work done by a isobaric gas, which means P is constant. Okay, B is constant. Okay, so B is constant. By changing, we can calculate its work done just by looking at how much volume changes. Okay, so V is volume. So pressure stays the same. If it's expanding without changing pressure, that's doing work on it's slowly spreading out, pushing out its space. Okay, therefore it's doing positive work. Okay, if the pressure doesn't change but it's shrinking, which means the surrounding have higher pressure, has forces causing to shrink, so it's doing negative work. Work's done on it. All right, and the temperature, of course, changes depending on it's shrinking or expanding. Okay, of course, if it's shrinking, it's going to heat up because you're doing work to it. You're adding energy to it. It's going to cool down when it expands because now the particles get further apart and further apart, and they're not colliding as much. Then the speed is going to slow down a little bit. All right. So, and of course, the energy is lost to the surroundings, right? Doing work to the surroundings, you're losing energy as well. This one you actually seen earlier, except it's not change. So this is change internal energy. Change in internal energy. I will not explain this more because it's the same, just changing temperature. All right, the next two are quite interesting. Both of these deals with entropy. So this are what we call the second law of thermodynamics. Well, related, but not quite what it is. Okay, that says in a system, okay, delta S is generally positive. Okay, but not always. Okay, these two formulas only tells you how to calculate. Okay, how to calculate. If you have a isothermic gas, okay, isothermic gas could expand, could shrink, and isothermic gas energy can still be exchanged for endothermic gas, right? And if there is energy added to isothermic gas, right? Temperature does not change, so it must be expanding or changing volume. Something's gonna the pressure and the volume will change, which means it's actually getting more random. So the first one is the entropy of an isothermic gas. The formula is what speaks for itself. Okay, delta S is entropy. Generally positive, not always, so do not say it's positive. It's negative, possible. Okay, the first one is the entropy. Got the O. Entropy of a isothermic gas. While the second one is how to actually calculate entropy. Change entropy. Next one is what entropy actually is, which is Boltzmann's constant times number of microstate. Well, omega here is the number of microstate. You may have to do a little bit of counting to count how many microstate there are. Okay, but they are usually not very simple. I may have given some more complicated ones that requires combinatorics just for fun. Okay, but IB exam, I do not foresee they'll give you a complicated combinatorics question to calculate number of microstates. All right, talk about isobaric. We talk about isothermic, and they are also isochloric, which is isovolumetric. That one is not really discussed on the formula sheet wise, but that's a process you also need to know. All right, and last one, of course, we looked at is adiabatic. Adiabatic means PBT are all changing, but there's no thermal energy added. So this is adiabatic process. Okay, during adiabatic process, PV is no longer constant because temperature is also changing. Instead, PV 5/3 is constant, but delta Q equal to 0. There's no heat during this process. There's some energy, but it never changes. Right? There's no heat during this process. So what happened is it will look like that, which finally leads up to a quick sketch of the four type of graphs. So if you have PV diagrams, pressure, volume. Oh, taking some time to process what's going on. All right. So P, V. So isobaric, constant pressure. Isovolumetric, constant volume. Isothermic, PV changes, but 1/P. So P is 1/V. This is isothermic. And then adiabatic, all three changes, and it's 5/3 bigger than 1. So adiabatic is steeper. All right. So I will not label. I'll label them quickly here. Isobaric. Oh, separate automatically. I don't know why. Isothermic. And isovolumetric. And of course, area under the graph is P times V. So area under this graph is work done. Going from left to right, you're expanding in volume. Positive work, right to left, negative work. Then you can talk about thermodynamic processes. Last two has something to do with engines, specifically how effective the engine is. Efficiency, of course, is useful work to find input, useful over input, useful work over input. Okay, but this ideal engine where the energy is 100% conserved, no loss in energy whatsoever, you don't have to add energy or remove energy to a system, it's self-sustaining, then basically all the energy not used to heat up the substance is used to do work, basically, right? So Carnot engine is equal to 1 minus Tc over To. So I'll write down a definition here. So this one is just efficiency. We've seen this already, but this one is specifically the ideal efficiency. It's not 100% efficient because some energy will have to be used to heat up the gas and cool down, and some energy will be cool down the gas, right? It's only the parts used. Carnot engine, okay, Tc is a hot cold temperature. Th is called hot temperature. You cannot get more efficient than this because, like I said, you need at least the amount of energy to heat it up or cool it down. Everything else is used to expand or shrink already. So that means you cannot get more efficient. So this is as efficient as an engine can possibly get. And that wraps up Unit B.